Sweet. Okay, so last time I left us with 4 theorems that we have to prove. And maybe you gave them a shot. Maybe you didn't. Realistically speaking, I'm not anticipating that you did. But that's okay, right? We'll take them up. And I literally just checked if you worked, and now it's not working. Maybe I should buy a new one for next year. Okay, so the first one we're going to do, I don't remember the order I gave them in. I think the first one was maybe what, you're convergent if and only if all subsequences are convergent. So let's prove that one. One direction is actually, it's funny, almost all students kind of screw up one direction. One direction is actually really easy. So let's do this one first. So a sequence AN is convergent if and only if every subsequence is also convergent and has the same limit. Okay, so let's prove this. So I'm actually going to prove the backwards direction first, just because that's the easy one. Right? So we're going to assume that every subsequence is convergent. Every subsequence is convergent. Okay, so this feels intuitive, right? Like you're like, oh yeah, okay, if all the subsequences, converge, then I should be able to force the original sequence to converge. Now, there's kind of a cheaty thing to do here, which is namely, the original sequence is a subsequence of itself, right? Is a subsequence of itself, and so hence converges. Okay, now that might feel a little shady, but it's totally legitimate within the scope and statement of our theorem. Now, if you don't like that, you can try and prove it and say like every strict subsequence converges, implies that the original sequence converges. That's also true, but it ends up being a little bit more work, and you don't really win anything from it. So this is sort of like the standard proof of this, and you're allowed to totally take this to be true. Now, the more interesting direction is the other direction. Right? So we're going to assume that the original sequence is convergent and now prove that every subsequence is convergent with the same limit. So let's give this limit a name. Suppose that AN converges to L. Okay, so the crux of the argument, subsequences should converge faster, right? If you think about it, what we're saying with the sequence is if you create some sort of epsilon ball or some sort of epsilon interval, if you go far enough into the sequence, eventually all of your sequence elements are in that little epsilon ball. Well, subsequences throw some things away, right? They just pick out some of the elements of the original sequence, they maintain the order, but for the most part, they throw elements of the sequence away, which means they'll actually get to the inside of that ball even faster than the original sequence will. So for that reason, from an intuitive viewpoint, what we're going to say is, oh, well, if you find an N that works in the epsilon delta definition, quote unquote, that if you find one that works for the original sequence, it should also work for a subsequence, and that's going to be true. Okay, so let's say let epsilon greater than 0 be given. And let's fix some N such that if N is bigger than N, then AN minus L is less than epsilon. Okay, so we claim the same N works. So the same, or you know what, here, let's fix now a subsequence. A sub n sub k. Okay. Now, the critical point of this argument is something that you have to, I think, sometimes bugs some students, but it's basically what I said about subsequences converging faster. Note that n sub k is always greater than or equal to k. Okay. Or maybe let me write this down in sort of like the function notation. N of k is greater than or equal to k, like that. Okay. And remember, when we defined a subsequence, we said you've got this map from the natural numbers to the natural numbers, which is strictly increasing. And so a strictly increasing map from the natural numbers to the natural numbers must have this property, right? It's impossible for n of k to be smaller than k. Why? So 1 has to map to something. The smallest thing 1 could map to is 1. 2 has to map to something. Now the smallest thing that 2 could map to, well, it has to be bigger than 1. So what's the smallest thing it can map to? Well, the answer is 2. So in fact, usually this is a strict inequality. N of k is usually strictly greater than k, with equals if and only if n is the identity map. Okay, so if you want to try and prove that, it should be a relatively straightforward induction proof. It's not terribly hard, but this is really just the statement that the index of the subsequence is always further ahead than the original sequence. And that happens precisely because, again, we kind of like threw out elements of the original sequence. Okay, so we note that n sub k is bigger than k. And so if what I want to say here, if n sub k is bigger, no, if k is bigger than n, right? Then n sub k is bigger than or equal to k. It's bigger than n. And so ANK minus L is less than epsilon. Right? And so there we go, we've proven it. So there's almost nothing to do with this proof. It's just the simple fact that subsequences converge even faster, right? And again, you can see this because we were able to use the exact same value of n. Okay, any questions about that one? Did I say I was going to prove the thing in green again? Okay, sure. So like the thing in green is just the functional equivalent of the statement to the left of it. So is it the green notation, or is it like this fact that n sub k is bigger than or equal to k? Just the notation? Okay, so remember, we might have to look at our notes from the other day, but a subsequence corresponded, no. So a subsequence corresponded to a choice of map, right? And map to n, which was strictly increasing. Right? And then you look at the sequence A compose n. And then we would write a, yeah, okay, good, cool. Yeah, so yeah, it's probably not too bad once we see like, oh yeah, okay, it's a map from the naturals to the naturals. That's why NK is bigger than K. Yeah, exactly. Okay, cool. So next up, I don't think I'm going to prove monotone convergence. I think you all know that proof. And if not, again, you proved it in term test 2 or something, right? So the monotone convergence theorem is a very straightforward proof. That one you should do, because again, you have done it. I think I've actually made you do it possibly twice. So I'm going to skip monotone convergence theorem. And again, that proof is identical. That proof is identical to what you did in test 2. Okay, it's just you replace the functions with sequences, and that's it. So let's do every convergent sequence is bounded. if there's time, maybe I'll do monotone convergence, but I don't think we need to. So every convergent sequence is bounded. Okay. And again, importantly, this is not true for functions, right? Because what could happen is you could have something like what? Like x, or maybe I should, no, let's kind of talk about this now. So let's say something like note pen. So what could happen is your function could have something like a vertical asymptote, right? Because when we take a limit as x goes to infinity, we're really looking at the horizontal asymptotes, right? We're looking at what happens as x goes to either positive infinity or negative infinity, but let's just pretend we're looking at positive infinity for now. Well, your function could have a horizontal asymptote, but it could also have a vertical asymptote, which guarantees that your function is not bounded. And that, is why it won't happen for functions, but it does happen for sequences. So note, this is not true for functions from like R to R, right? For example, we could have something like f of x. What do we want here? Let's do something x plus 1 all over x minus 1, right? This function definitely has a limit as x goes to infinity. Oop, just threw my pen because I'm so angry at it. So this thing has a limit as you go to infinity, right? It's actually equal to 1. But it's definitely not bounded. Right? You could probably make some sort of argument that it's eventually bounded, because of course that's certainly true, right? It's eventually bounded because just by the epsilon delta definition, if it converges to 1, eventually it always has to stay within a little epsilon band of 1. So it's definitely bounded around 1 eventually, right? But it doesn't have to be globally bounded. This theorem that we're about to prove says that sequences have to be globally bounded. And think about why that's true. So the fact that our domain is discrete, right, means that my function can't have vertical asymptotes. Like that's just not possible. How do you like shoot off to infinity at a finite number? Like what would it mean to have a vertical asymptote at the number 5, right? Like you've got a sub 4, you've got a sub 6, and you've got a sub 5 in between. All these numbers have to be finite. They can't like shoot off to infinity. So the only way that a function can be unbounded is as it goes off to infinity, right? It'll do something like whoop, ramp up or whoop, ramp down to negative infinity, something along those lines. But that's the only behavior it can have. That's the only way it can fail to be bounded. So if we start with the assumption that our sequence is convergent, it can't shoot off to infinity, right? It has to be bounded everywhere. And that's the basis of this theorem. Okay, so if we prove it, what we're going to do is let's start by choosing. Oh, I guess we should give the sequence a name and give its limit a name. So let an be a convergent sequence, and let's give its limit equal to L. Okay. Let's let epsilon. Let's just pick an epsilon. We know that it converges. So let's pick epsilon equal to 1 and choose n in n such that the usual thing. Oh, less than 1, right? Okay, now the critical thing here, this is sort of even what I was saying with the function, right? Eventually you have to stay within your epsilon band. So let's unravel this definition, the absolute value here. we get that L minus 1 is less than AN is less than L plus 1. Okay, so this doesn't tell me, of course, that the sequence is globally bounded. It tells me it's bounded after N, right? Thus, the sequence is bounded after N. Now, our argument from here is relatively straightforward because we say, well, therefore, there are exactly N other points of the sequence, right? The beginning of the sequence has exactly N points left over, and they all have to be finite, right? None of them can be infinite because you can't have, your sequence take on infinity as a number. Like, that's not possible. So it has to be bounded because we can just take, for example, the maximum of, if we're looking for an upper bound, we can take the maximum of L plus 1 and any of our previous elements, right? So set let's take the max. And little m to be the min. And now we are guaranteed that AN is always between little m and big M. All right, so that for all natural numbers, right? And hence is bounded. And you can see like why this proof wouldn't work for functions from the reals to the reals, because once you say, okay, I've got this point after which I know I'm in the epsilon band, that's great. I've bounded after that. But before that, anything could happen, right? The function could exhibit any sort of behavior. The important and critical point here was that, okay, we're bounded after N, but there were only finitely many things we had to worry about before that point, right? That's it. With a function from R to R, you have uncountably many things, right? You're kind of screwed. There's nothing you can do. Yeah, we did. It was, let me see if I can hunt it down. I think right here. Yeah, it's 1. Do you see it? And is bounded from above / below, and then it's bounded if it's bounded from both above and below. Unless, Stephen, did I misunderstand you, or is that answer your question? Right? It's sort of like the usual definition, right? Where you say there's something above it, something below it. All right, so I'm going to assume you'll let me know if I didn't answer that. Oh, okay, sure. Yeah, so, but you're okay now? Yeah, okay, cool. All right, so now finally, our biggest and most important one, which, again, we ended up talking a fair bit about sort of even on Tuesday at the end of class, which is the following. So a function from R to R is continuous at a point C if and only if whenever AN is a sequence which converges to C there really should be another set of brackets around here, but I think it's starting to get like busy with brackets. F of AN converges to F of C. Okay, so this is equivalent, right? Look, it's an if and only if, which we know means logical equivalent, but there's no additional assumptions in the first statement, right? A function is continuous at C. there's no additional assumptions there other than the fact that f is continuous, which means this is an equivalent definition of continuity. This is also what it means to be continuous. And you could, if you wanted to, define continuous functions this way instead of using the epsilon delta definition, that we did back in the day. So this is a thing that we can do. The proof of this isn't too bad. The proof of this, I think this looks scary, but the proof really isn't too bad. So let me kind of give you an idea of what this looks like. Now, this might be a little bit hard to visualize simply because, no, exactly. It is exactly a topological definition of continuity because sequences are themselves a topological notion, right? And so it is precisely like, usually when we think about topology, we often think about like open sets and things like that, but sequences are a characterization of openness. Usually it's actually a characterization of closedness, but we know closedness is just the complement of openness, right? So sequences is really how you characterize whether or not a set is closed. And in fact, I can give you that definition in a second, or that theorem in a second, but sequences are how you characterize closedness. And just as the preimage of an open set being open is equivalent to continuity, you could have equivalently restated that as the preimage of a closed set is closed. And so there is a very real sense in which this is precisely capturing that information. Yeah, so it does feel very similar to a topological definition, and that's because in many ways it is, right? The only sort of thing you kind of have to worry about is if you go and you do like really abstract topology, you might not have sequences. The best thing that you might have is something called a net, but I'm pretty sure the continuity definition on nets is still true. Okay, so let me draw a big old picture here so you can see what's happening. And on Tuesday, I said that we could visualize sequences in two different ways. This one's going to be maybe a little bit confusing because we're going to do both of them simultaneously. Okay, so I'm going to try drawing my picture really, really big. Okay. And let me draw a function here. Okay, so here's y equals f of x. And let's choose our point C. All right, so let's choose our point C like here. L like that. Okay, and let's just draw an epsilon delta ball like we normally do, right? So we're going to do something, and I'm going to draw, again, quite big so that we have lots of room to work with, just when we're visualizing stuff. So C minus delta. Right, and then we might have like an epsilon ball, something like this. I guess I need to make epsilon even bigger. So okay. So what we're going to do is we're going to visualize this by looking at, I need a different color. Maybe now is a time, do I have rainbow set up? Maybe not. Maybe we'll just do black. No, we'll do white. Okay, so along the x-axis, remember when I said you could think of it in terms of the graph, or you could think about it just in terms of its image last time. So the x-axis is the image, right? So we're going to look at a sequence that converges to the point C. So maybe it starts originally outside, right? Like maybe here's A1, and then we jump inside, we got A2, and then we start to get closer to C, right? So maybe it oscillates back and forth, but eventually it starts to narrow in and it converges to the point C. What we want to do is we want to look at now the image of these functions. So we're going to look at f of these things, which is going to be now the image set picture is going to be on the y-axis, right? So I'll get something like, here's f of A1. A2 is somewhere around here. A3 is somewhere around here. F of A4 is somewhere around here. right? And so on and so forth. And you can see, again, it's sort of like they're starting to converge in on L. So what we're going to end up doing is we're going to use delta as the epsilon ball for the sequence, right? So remember, we know that the A's converge to C, which means I can guarantee that they always live in some sort of epsilon ball. The epsilon that I'm going to choose is actually going to be the delta. And if I can guarantee that the A's live in the delta band, that means that f of A's will live in the epsilon band, right? And that's what I want to do. I want to show the f of A's converge. So I want to show that they get to within epsilon of L, which means I need to show that the A's get really close to C. And how close? Well, the answer is delta close. Okay, so hopefully if you think about that for a second, it'll make sense. I want the F's to get close to L. How do I do that? And make sure the A's get close to C. And the definition of continuity, this is the forward direction. The definition of continuity is going to give me the tools to do that. It's going to give me an epsilon and a delta. And those are my two things that I'm going to use for closedness. Okay, so hopefully that makes sense if you think about it. Okay, so let's do the following. So fix a sequence. Oh, sorry, I should say we're proving the forward direction. So forward direction. So it's a fix a sequence A sub n, which converges to C. Again, what are we trying to prove? We're trying to prove this bottom thing here, which is at the top of the screen. We want to show that f of A n converges to f of C. So let's let epsilon be greater than 0. Okay, so I've now fixed, if you think about this as a picture, right? I fixed my sequence and I've let epsilon be given. So I've figured out what my epsilon band is on the y-axis here. So now I'm going to use the definition of continuity to get a delta band. Since f is continuous at C, there exists a delta greater than 0 such that if x minus C is less than delta, f of x minus L is less than epsilon. Sorry, f of C. Still, my brain is working in general limit mode, but we're talking about continuity here, so we know exactly what the limit is, right? Okay. And now, so again, I've specified what my epsilon band is on the y-axis. I now have my delta band on the x-axis. And what I want to do is I'm just going to say, listen, I know that the A's converge to C. So there's some n big enough that all but finally many of the elements of the sequence live in that delta band, right? So choose n in n such that n greater than n then an minus C is less than delta, sorry. And now we're done because an minus C being less than delta implies f of an minus f of C is less than epsilon. Right, for all n bigger than n. And that's what we wanted to prove, right? That's the definition of FAN converging to f of C. We fixed an epsilon, we were able to find a capital N such that beyond that, all the FANs are within the epsilon band of f of C. So boom, we're done. Okay. So I got to prove the opposite direction, but let's just stare at that for a second. Let me know if you have any questions. Again, I think that's like deceptively straightforward. We didn't set delta to be epsilon anywhere. It's that like delta, okay, so I fixed the epsilon, which is the the band on the y-axis. I use continuity to get the delta on the x-axis, and then I use that delta for the sequential epsilon, if that makes sense. Like I just said, I want to make sure that my sequence elements are within that delta band. So I'm going to choose an n big enough to make sure that they're within delta of c, right? So I guess that's like setting delta to be epsilon, but there are two epsilons here. One is the epsilon for the continuity of the function. One is the epsilon for the limit of the sequence an. And I've said I'm going to use delta instead of epsilon for the limit of the an. Yeah, but they could be different, right? The delta and the epsilon that I've given here, really, again, they depend on the function. Okay, does that make sense? Everyone's okay? Okay, sweet. So our next step now is to prove the contrapositive. And the contrapositive is, or rather the opposite direction. So look at the theorem statement. It would say that if basically if your function preserves convergent sequences, if it takes convergent sequences to convergent sequences, then you're continuous at that point. And you might be tempted to try and prove this directly, but of course this is a nightmare because you're going from discrete information, right? Something about sequences, and trying to prove something about the limit of the function. But the function is a very, its domain is uncountable, right? Even in an arbitrarily small neighborhood around your limiting point, C, there are more real numbers in that band than you have sequences. And in fact, if you took countable number of sequences, they still only consist of countably number of points, right? So trying to use discrete information to infer continuous stuff, very difficult. So in these sorts of situations, the hint is basically, since that's impossible, don't try and derive information about discrete things into continuous things, but instead do the contrapositive. Okay, so we're going to prove the backwards direction by the contrapositive. Okay, so I'm going to say by contrapositive, what does that mean? So we're going to assume that f is not continuous and show that there exists a sequence which converges, but its image does not converge. So we proceed by contrapositive. That is, we'll assume that f is not continuous and show that there is a sequence an which converges to C, but f of an does not converge to f of C. Right? So again, maybe let me zoom out so we can see the original theorem statement and you can convince yourself that this is in fact the contrapositive, right? We're going to assume not P implies not Q. So we're going to assume that F is not continuous, and that implies not the bottom statement. So the bottom statement is that if AN goes to C, then F of AN goes to F of C. The negation of that would be a counterexample, right? The negation of that would be a sequence which converges, but f of it does not converge. Okay, and again, hopefully you see, is everyone okay with like that this is the thing that we're trying to prove, that this is what the contrapositive is? Let me know if not, because I can try and break it down into like more logical steps. There's a lot of like implication arrows going on here, right? It's if f is continuous, then if AN converges to C, then f of AN converges to f of C. So there's a lot of implications there. We're trying to do a bunch of negations. It's a little bit tricky, but hopefully this makes sense. And the next step is to try and see that the definition of not continuous is exactly what we need to prove this. Okay, so try like try and think about why that would be true. So I'm confused. Continuous implies, no, right. So yeah, let me maybe put this logical statement up here in a different way. So it's sort of like continuous at C implies AN converges to C implies f of AN converges to f of C. Or maybe, so as a theorem statement, sort of written only in terms of symbols, right? Yeah, does that make sense? And so not this is AN converges to C and not f of AN converges to f of C, right? And that is the counterexample, right? We're trying to show there is a sequence which converges to C, but f of AN does not converge to f of C. I'm getting a little bit messy here. For the record too, this is sort of a common abuse of notation. So technically speaking, right, if we look at this thing right here, the f of AN should be in brackets to indicate that it's a sequence, but often we just kind of are like, okay, there's too many brackets. And we just say, listen, we know that this is a sequence. And we'll just write that. Again, strictly speaking, that's bad, right? That's a real abuse of notation, but we do sometimes do it. Okay, so if you see me do that, don't get too upset with me. And so you can see I've done it here, for example. Okay. Now let's write out the definition of not continuous, right? So since f is not continuous at C. So remember, there's a bunch of quantifiers here, but when you negate a quantifier, you just flip it, right? So for all becomes an exists becomes for all. So f is not continuous at C is there exists an epsilon such that for all delta greater than 0, there exists an x in R, x minus C is less than delta, and f of x minus f of C is greater than or equal to epsilon. All right, so that's the definition of not continuity. I took the definition of continuity and negated it, right? I flipped all the quantifiers. And then again, here we would normally have x less than C less than delta implies f of x minus f of C less than epsilon. So the negation of the implication is P and not Q, namely x minus C is less than delta and not f of x minus f of C is less than epsilon, right? And again, hopefully you're looking at this and you can see this is exactly what we need. This right here is how we're going to guarantee that we can find a sequence which converges to C. Use to find an AN which converges to C, right? Because this holds for all delta. It says no matter what delta you choose, you can find some point X, which is arbitrarily close to C, but f of X is far away from f of C. So I can make the X's converge to C, but the f of X's not converge to C. And then f of AN will not converge. Do you kind of see like how that's going to work, right? So what I'm going to do is I'm going to say like, let delta be 1 over n, right? So, let this epsilon, let's say, fix that epsilon in this definition. Let's say to show that f is not continuous. And then what we're going to do is we're going to say for each natural number, let's let delta n be 1 over n. Okay. Now, according to this definition, so I've got the epsilon, which satisfies, maybe let me give this a name. Let's call this star. Okay, so epsilon satisfies star. I've chosen a delta to be 1 over n. So according to the definition of not continuous, there is a point such that that point is within 1 over n of c, but f of that point is further than epsilon from f of c. So define a sub n to be such that and f of an like this. Okay, and we're just do that for every single natural number. So we're done, right? So claim and converges to C. This is pretty easy. So let epsilon hat be greater than 0 and choose n and n such that 1 over n is less than epsilon hat. If n is bigger than n, then an what do I want here? So I chose an n, 1 over n is less than epsilon. Oh, yeah, I'm done. Right? Because by definition, you chose the ANs such that they were a distance less than 1 over AN from C. So if you go far enough down the sequence, yeah, you're definitely going to be less than some fixed epsilon, right? So the ANs definitely converge to C. And now we claim f of AN does not converge to f of C. There's almost nothing to do. I almost just want to leave this as an exercise. Look at it. By definition, each of these things is bigger than or equal to some fixed epsilon. So you can easily, whether you want to prove directly from the definition of a limit not existing, or you want to do a contradiction proof, you can be guaranteed f of ANs don't get arbitrarily close to f of C, right? There's almost nothing to do. So maybe let me just leave this as an exercise. It's up to you. Okay, if you want to do it as a contradiction, that's probably the easier way. Or if you want, write out the definition of limits converging and take its negation and figure out what that definition is and prove that it satisfies that definition. But it almost immediately does. In fact, here, why don't we do this right now? So the negation, the statement, AN does not converge to C is there exists an epsilon greater than 0 such that for all n in n, there exists an n bigger than n like this, right? And you can see, you're done. F of an is always some distance away from f of c. So there's nothing to do. Yeah, it doesn't matter what n you give me. Every single one of these points is further than epsilon away, right? So this epsilon does the trick. Yeah, I might as well just write that out. Let epsilon be as above, and n in n arbitrary. Choose, let's say n to be n plus 1. It doesn't matter, right? Literally, they all work. So choose n to be n plus 1 so that n is greater than n and f an minus f of c is greater than or equal to epsilon. And that's what we wanted to show. Okay. So ironically, I guess it's the opposite direction, which is actually sort of the tougher direction. And I don't think it's actually tougher. It's just more of like, because everything is negated, it's a little bit more abstract, right? There's a little bit more thinking involved because we're not used to dealing with the negations of these sentences, right? Like we're not used to dealing with, oh, this sequence doesn't converge or this function isn't continuous. Those are sort of weird to us. So I went a little bit slower there and really tried to spell out what was happening. But the reality is that we could have done this proof in roughly the same amount of work as we'd done the previous one, right? Like look at the size comparison between these two proofs. But no, we could have done the backwards proof in roughly the same amount of work. I wanted to really go a little bit slower just because we're not used to that. But it's basically the same, right? Especially if you don't prove these last two claims. I personally think these last two claims are obvious, right? I made sure the ANs got close to C, and I kept the F of ANs far away from F of C. So ANs clearly converge, F of ANs clearly don't converge. Okay, are there any questions about that? Again, I think the backwards direction looks worse than it is. If you're like, oh man, how would I ever come up with this? It's mostly just writing stuff out, right? There actually isn't a lot of math there. Everyone good? Hopefully that's all right. Okay, I'm going to assume that it is because I don't hear any major protests. All right, that's going to take care of it for today. Let's see. Important announcements. Obviously, test 5 is going to go live tonight. It'll be a fun test. I'm excited for it. Next week, honestly, I don't even remember what I put on it. Is there anything interesting? There's one really cool question. Like yeah, let's see. Let me put the following. Question 3 is so cool. I think a lot of you, it's not like, I don't think it's terribly hard, question 3, but I think if you look at question 3 and you're like, this is awesome, you're like, I hope that you'll have that realization, assuming of course that you get it. I tried not to make that question too hard, but it is an awesome question. I think question 1 is the hardest. So this is kind of like a warning, is that don't see question 1 and be like, oh God, like the rest of the test is so bad. The test ironically might be hardest to easiest, if that makes sense. So you might actually want to start at question 3. I think question 1 is the hardest, question 3 is the easiest, and question 2 is in between. No, there aren't many hints, I think, to give. You know, question 1 has 2 parts. There's a non-trivial amount of substitution and integration by parts, for sure. You know, part 1 has 2 parts, and if you can't get part A, don't freak out. You can use, it's designed so that you can just use part B. Okay, so if you can't get part A for whatever reason, you can just go straight to part B. Question 2, I legitimately don't even remember what I put for question 2. What did I put? Oh, question 2. Question 2 is pretty easy too. In fact, we did a lot of question 2 in class. And in office hours, actually. So question 2 might be the easiest. So question 2 and question 3 are pretty straightforward. Question 1 is the only, I think, one there that's actually a little bit tricky. And if you've done a lot of practice, I don't even think it's that bad. So you can tell me next week how terrible it was. But I think all things considered, yeah, we'll see. No, because I had made the test. I made the test before the reading week. So the fact that we had talked about something in office hours is actually just you guys like getting lucky and honing in on a couple of things. But yeah, we'll see. You can tell me. You can yell at me at Tuesday and you're like, oh yeah, that wasn't anything like what you said it would be. Okay. All right. So good luck, everyone. I don't think you'll need it. No, not yet. Actually, I did get an email, but I haven't read it yet. So I'll have to see what he said. Yeah, no problem. Thanks, everyone. Thanks for coming. Yeah, like I said, good luck tonight/tomorrow. Don't forget, you can ask stuff on Piazza, and we'll do series and stuff next week. Okay. Bye, everyone.